So on Monday, we got started with strengthening, and we reviewed subsystems in FCC and BCC and HCP, and talked about the Schmidt law, and that anytime you deform a crystal and there's some sort of confinement, you're changing causing the lattice to rotate in some way, right? When we think about a single crystal, right? Single cubic crystal, and the cube faces are aligned, so I have a perfect 100 crystal. If I just shear that and I pass a dislocation from one side to the other, I've created a step in that interface, but I haven't caused any lattice rotation, right? I mean, I still have a perfect lattice everywhere except for that tiny little step, right? And I can pass as many dislocations as I want on that same plane. And all I'm going to do is make that step larger and larger and larger, right? It's only when you have some sort of confinement that you end up with the rotation, right? Here, if we think about a tension test on a single crystal, the grips are offsetting that shearing, right? Our grips remain parallel, right? And so we're going to be causing a rotation. In a polycrystal, the neighboring grains give you the confinement, right? And so an idea here is anytime you have confinement, you're going to have a rotation of the lattice. Anytime you have a gradient of strain, you're going to have a curvature of the lattice. And this idea will come up later when we talk about other things. And then we said, well, we made the observation that strengthening is all about putting obstacles in front of dislocations. And if we want to talk about that seriously, we need to first talk about what's the force required to move an individual dislocation, right? And we introduced the notation of a Pierells stress, which is the intrinsic lattice friction for moving a dislocation. And we basically said that FCC metals are going to have we related, where am I going? Oh, that's the wrong way. No, that is the right way. Somehow I must have held my finger down. Right, we related this Pierells stress to the core width of the dislocation, and said that if our core width is really spread out, our Pierells stress is much lower. It's easier to move our defect. And if we have a highly concentrated, highly compacted core that you get in non-close path structures or highly directional bonding, like ionic or covalent bonding, you have very narrow widths and very large cores. And also the width of the core is going to be related to the temperature dependence of the yield strength, or the temperature dependence of the slip. And we left right before we looked at the explicit form for the Pierells stress. And for this course, we're not going to derive it, but keep in mind, what do we see here? It's exponential with the negative 1 over the Burgers vector, right? We've got a plane spacing in here, right? And we've got shear modulus out front, right? So it's interesting that shear modulus comes into this yield, right? Because you sort of think of elastic properties and plastic properties as being divorced, right? But this gives you a natural connection through the stress field around the dislocation and the elastic distortion caused by moving a dislocation over, making and reforming those bonds. That basically says that the higher the elastic stiffness of your material, the higher the yield strength is also. Right? So there's that connection that comes out. And that the wider your interplanar spacing is, the lower your Piral stress is going to be, the easier, the lower your yield stress is, and that the bigger your Berger's vector, the larger, right? So right out of this, we see the preference for close packed directions on close packed planes, because the close packed planes have the widest interplanar spacing, and the close packed directions have the shortest Berger's vectors, right? And so all that just gets tied up into the width, right? So that the bigger the core width, the easier, the lower your Piral stress is going to be, right? Okay. So just a little bit of a review. This isn't going to come up much. The important one here is the line tension on a dislocation, right? The strain energy per unit length, right? And it's the work that you have to do to increase the length of your dislocation line, right? So that means straight dislocations are energetically favorable to curved dislocations, right? Because you have less line length, right? And that's going to be proportional to GB over 2R. This I threw in here, the driving force for slip, because the only thing that's important for this class is that the force on a dislocation acts normal to the dislocation line, right? And so the resolved shear stress at each point is always going to be normal to the line, right? That's really the only important thing there for this class. Right. A couple other important bits, and a lot of this I realize is review, especially for the graduate students. This is like the umpteenth time you've seen these things. Some of the welding students may or may not have seen this before, right? So what's the implications of this energy, this GB squared term, right? And that's basically that dislocations in real metals never look like the regular perfect edge or screw dislocations that we talk about. Typically, they're dissociated, right, into partials. And we won't get much into the structure of those partials except with when we talk about nickel superalloys towards the end of the semester. But there is one really important concept that comes out of this, and this is the notion of stacking fault. And when you dissociate a dislocation into two partials, you create some kind of fault, right? You have a mismatch of your stacking sequence, right? So FCC is A, B, C, A, B, C, right? HCP is A, B, A, B, A, B. And when you have a partial, when you dissociate dislocations and one partial goes by and the other hasn't, you've created a stacking fault in between where you have a disrupted stacking sequence. And the amount of that, how high that stacking fault, the energy of that fault is going to determine how far apart these partials are. Are they going to be close to each other or well separated? Right? Well, why is this important? And it's because the stacking fault energy, as we'll see throughout the rest of this term, it'll come up again and again and again. It really relates to the fundamental deformation mechanisms that happen in the metal. Yeah. Oh, this is just if you have a perfect dislocation and it dissociates into two partials. So G here is again a shear modulus, directional shear modulus along the Berger's vector direction. Right. We can skip over. Right. I'm skipping over details because just a couple big ideas are really what's important here. And fundamentally controls how the metal deforms, the stacking fault energy, and as a function of that, how far apart these dislocations are, right? And so we see that different metals, aluminum has a very high stacking fault energy and a very low strain hardening, degree of strain hardening coefficient. Whereas stainless steel has a very low stacking fault and a very high degree of stacking fault energy and a very high degree of strain hardening. So how do these two things relate? Remember, we've got these partial dislocations that are separated, right? A partial dislocation, is it an edge or a screw, or does it have mixed character? Right? It's neither a perfect edge or a perfect screw, right? So it's mixed. So because it has edge character, what's the primary difference between edges and screws in terms of mobilities? Cross slip. Screws can easily cross slip. Edges have to climb to change planes, right? So when you have partials, they can't easily cross slip. They have to come back together to form a perfect dislocation to be able to cross slip. So does it make sense that if the stacking fault energy is low and these partials are very far apart, it's not easy for them to come back together to reform a perfect dislocation so that they can cross slip around some obstacle, right? Whereas in aluminum, the partials are very close to each other. So that means when they come against an obstacle, they can easily come together and cross slip around. So we see that as a difference between planar slip versus wavy slip. So this is aluminum. You can see these slip traces are not straight. They're curved and convoluted, right? That's a consequence of easy cross slip. Whereas in copper, well, this is planar, so this is probably a steel of some kind. We see much straighter slip lines. Right? And again, for the welding guys, don't get bogged down in the details, right? Right? Don't think, trust me on this, right? Don't panic, right? This is just sort of things that we're going to come back to, right? So by the end of the term, you'll be an expert on this stacking fault stuff. All right. Okay. Also, one little thing that we keep in mind is how do dislocations actually move, right? The whole dislocation line doesn't move at once, right? That's too much, right? Too expensive energetically. What does happen is a small region steps forward and makes a little kink, right? And then the whole line can move forward by essentially by the lateral motion of this small section here, right? So you're not moving this whole big dislocation line all at once, right? And the nature of this kink width is a function of the Pierells stress and the line tension of the dislocation. And like the dislocation width, the kink width, the more widely, the wider the kink here, the easier it is to move, right? Okay. So we're making progress through this. So that's sort of individual dislocation stuff. Now we want to talk about families, right, of dislocations and populations of dislocations. Right. So dislocations control almost all the aspects of strength and ductility in structural metals. Anytime we talk about yield strength, anytime we talk about ductility or toughness, right, we're always really at the end of the day coming back to dislocation motion. And so if we have a pure metal in the absence of secondary phases, we want to be able to relate the yield stress to the dislocation density, right? And this is what we have here is sort of the classic Taylor-Hardening relationship that said the yield strength is going to be proportional to the square root of the dislocation density, right? So as we know, the yield strength is controlled by the density of obstacles blocking dislocation motion. So a high dislocation density gives us a higher strength. The more obstacles, the more dislocations get tangled up, right? And so at stresses smaller than the critically resolved shear stress, these dislocations are only going to travel short distances before getting stuck at obstacles, either other dislocations, secondary particles, or interfaces, right? Above the CRSS, we inherently say there's enough force pushing on the dislocation to move them past the obstacles. So what do we mean to actually move past the obstacles? Yeah. M is a plastic modulus. It's not a Schmidt factor in this. This is a slide I took from other notes. This is actually a Taylor factor, average Taylor factor of all the grains, but we can ignore it. The most important thing is that it's proportional here to the square root of the dislocation density. Right? So these dislocations are not straight lines, right? Because they're not. A dislocation is not a line segment, right? Dislocation can't begin or end in a line, right? The easiest way to think of a dislocation is still it's a boundary between a region that has sheared and a region that hasn't sheared, right? So if you have a straight line that ends within the crystal, it's not a boundary, right? It doesn't enclose off some area that's sheared, right? Unless it goes to the edges, right? It can go to like the edge of a grain or the complete edge of a sample, right? But if you're within a single crystal, you can't have a dislocation that starts and stops. So they have to be loops, right? And so here we see a dislocation loop, and this is the region that has sheared, this is the region that hasn't sheared, and the Berger's vector has to be constant along the whole loop because it's the amount that this region has sheared, right? So the Frank-Reed source is a way of making these loops, which are then going to propagate out. You can imagine a short segment of a dislocation that's pinned at two obstacles here. And if we have a force on it, it's going to bow out, right? And eventually it's going to bow out and keep bowing out until these touch. If we think about the line sense on this, these now are opposite, just these two segments here have opposite sign. So they're going to annihilate in the middle, create a big loop with a new pin dislocation segment in the middle, right? And if the force keeps going, this is going to activate over and over again, and this Frank-Reed source is just going to pump out dislocation loop after dislocation loop, right? Expanding this region, the sheared region, right? So what's the force required to make that happen? Well, we can set up a simple force balance. If we have a distance here between these two pinning points, we know the line tension here, right? We can resolve the force in the vertical direction, right? And calculate the force exerted on the dislocation per unit length from our Petrikola equation. Again, this is something I expect you to know, to be able to describe the process, right? I don't expect you to actually, on an exam, I'm not going to ask you to prove the force to, the Boeing force to operate a Frank Reed source, right? Okay. So this gives us the total force on the pin dislocation, and everything has to balance, so we can come up with this relationship here, right? And basically, at the end of it, if we work through different positions on the loop and evaluate it, the largest stress is going to be required here at position 2, where the radius of curvature is the greatest, right? Because that's where the line tension is exerting the most, is maximum, right? And we can work through the math, and we can show that the Boeing stress is basically GB by the separation, right? And that if we have a force that's greater than that, we'll be able to push this all the way through and activate this stress, right? Right. So we can create dislocation loops. There's a whole bunch of different sources, right? There's people play with single arm sources, but the Frank Reed is sort of like the archetype way of doing this. You can also have sources that come up that connect the other end. You have one pin segment, the other end hits the end of the grain and swing around like pinwheels. People have come up with all kinds of crazy theoretical ways for dislocation loops to be generated. But just thinking about the Frank Reed source gets us 90% of the way there. Okay, I realize this is it seems a little sort of tedious and disconnected, but I want to make sure that we have a fundamental sort of picture of strengthening. Then when we jump into aluminum, we don't need to make too many diversions to talk about these things, right? This is stuff that's common across all the systems. So, right? Okay. Again, I'm repeating myself over and over again. Dislocations interact with obstacles, right? If we can rise above the Orawan-Boeing stress or the cutting strength of the material, let's just talk about the Boeing stress, right? The dislocation can get past the obstacle and travel across the grain, right? And we can think about this in terms of the obstacles being precipitates or other dislocations, right? For weak obstacles, we don't need, if our obstacle is fairly weak and easy to get around, or easy to cut through, we don't need to go all the way to this semicircle configuration, right? We can cut through at a lower degree of curvature, right? So if we have weak precipitates where the cutting strength is less than the Boeing strength, we don't need to actually get all the way here. We can cut through earlier. Okay. So again, the strength, if there's one thing you learn, it's the strength of a metal is increased by putting in obstacles that impede dislocations. So if we think about obstacles that are fairly strong, right? We have an effective length that's approximately equal to the actual length, right? If we have a dislocation that hits up against these strong obstacles, the real distance that we care about is the separation, and our analysis for the Frank Reed source Boeing holds just fine. If we have obstacles that are easier to cut, our dislocation line remains straighter. So our effective length is not really the length between the obstacles. It's approximately the straight line length between obstacles, right? If we have strong obstacles that are enough to really pin, our dislocation line first kind of gets stuck, and then it bows out between each set of these pinning pairs, right? And so the effective pinning length is really the separation between those particles. But if we're easy to cut through, we're not bowing out a lot between the particles, right? Our dislocation is straight, relatively straight, and then it hits these particles. So it's really like this straight line distance, which means that the strength provided by these weaker obstacles is significantly smaller because this critical angle remains relatively straight. Right? Okay. So there's a lot of details I'm sort of skipping over in the derivations. And again, those derivations are not important. These particular final expressions are not important for you to memorize, right? It's just this idea of that when the obstacles are weaker, the dislocation line remains straighter, right? And the distance between pinning points is much larger than the effective obstacle space, or the actual defect or pinning point spacing. Whereas for strong defects, it is actually the particle separation that matters, right? So if these are particles that need to be bowed around, right, versus particles that are easy to cut. And in aluminum, we'll talk about this in terms of, say, these will be GP zones, and these might be coarse intermetallics, right? So, okay. So stage one, we showed this picture before. This is a single crystal, and we said we broke it up into stage one, easy glide, and then this work hardening regime, and then a stage three, right? So in easy glide, there's very little hardening that happens past yield. That's because we don't have enough dislocations to interact. The dislocations, once they get moving, are just free to keep running because they're not hitting anything else, except maybe some grain boundaries. Well, it's a single crystal, so they're not even hitting grain boundaries, right? But they're not interacting with other defects. At stage two, we see dislocations that interact. What happens when you have two dislocations that run into each other and they cross? You can get jogs, right? And jogs are not easy to move, right? They have edge components. They have, right? They have potentially have Burger's vectors that are not well aligned, right? To move in the same direction as the resolved shear stress. So these jogged regions need to be circumvented by bowing or extrusion, right? And we can derive this same Taylor hardening expression from the jog spacing, right? And I say homework, but that's just because I forgot to take that out from when I used these notes for a previous class. All right. So this is the intrinsic strength of the material with a low dislocation density. So this is going to be proportional to the Pierells stress, right? How easy the defects are to move. And this alpha is the degree of is a factor, and they're going to be different from all the different metals. But for FCC, it's definitely smaller, typically smaller than BCC, right? And this has to do with the number of different slip systems available, right? So BCC metals will tend to work harden more than FCC metals. Is the takeaway there? Right. And this square root behavior is observed over many orders of magnitude for dislocation density, right? This is 10 to the 15th. What are the units for dislocation density? It's per meter squared. So where does that come from? It's line length, which is meters, per unit volume. So it's meters of line length per volume. So meters by meters cubed gives you per meter squared. So for a sense of what these numbers mean, right? Okay, 10 to the 10th. This is super low, right? But how low is it? How much dislocation, right? What is 10 to the 10th meters? How far is that approximately? Right, so if I had a chunk of well-annealed metal that would fit on this tabletop, right? 1 meter by 1 meter by 1 meter. There's 10 to the 10th meters of dislocation line in it. How far would that go? It's like roughly the distance from here to the sun, right? A lot. So even in really well-annealed material, there's a ton of dislocations. A huge amount. What about you go to the other extreme end? What's the most that we can really physically pack in? If you do like shock loading at cryogenic temperatures, what kind of dislocation densities can you come up with? Well, this chart goes up to 10 to the 15th. Do you think we can get better than that? Would you guess maybe we could get 1 order of magnitude better than that? Like get something that's about 10 to the 16th? Probably. What about 2? That would be really pushing it, right? 100 times the biggest thing on this chart, right? So say 10 to the 16th is kind of our upper limit. What kind of distance is 10 to the 16th meters? It's far. It's like a light year.
10 to the 10 is 6.2 million miles.
Yeah. Right? And 10 to the 16th is the amount, the distance that light travels in a year. Right? And that's how much line length there is. Right? Defects, the dislocations are ubiquitous. Right? Think about the amount of volume you look at in a TEM foil. There's a calculation that was done in the 80s that said in the first 40 years of the TEM, the actual volume of material looked at was about the size of a head of a pin, right? Because how thin are TEM foils? They need to be electronically transparent. So say on average 50 to 100 nanometers thick, right? And the amount of distance that you're actually irradiating on that foil to look at, right? So the amount of material actually imaged in TEMs were vanishingly small. But guess what? We see dislocations all the time, right? So there's a ton of them, right? This like as a mechanics person completely amazes me.
This is experimental data.
This is experimental data, yeah.
I mean, how are they even measured?
You can do it from peak broadening in X-ray. You can get estimates that way. You can also cut up foils and look at how many I see, and then calculate how much would be lost due to image forces, right? Because when you have forces from the surface acting on the dislocation, so you can calculate how many were lost from your foil due to that, then count how many dislocations you have, knowing the volume that you're looking at, right? So it's a lot, right? Okay. So this next bit here, this is really just for your information. This is just how you can arrive at this square root row dependence based on stereology, right? How can we, if you think about the distance between dislocations and the curvature and the amount of area swept out by a growing loop. And it's not a hard calculation, so I threw it in there just for your interest. So what is, just for the point of it, what is stereology? Has anyone heard that word before? Right, it's the estimation of 3D information from 2D cross sections. Right, and there's some fundamental ideas that the number of points per unit line is going to be proportional to the number of points per area. Right, if I have lines and I make a 2D section through it, the number of points that I see is going to be proportional to the line length per unit volume in my sample. Right, the number of points it's like the flux of lines that cut a plane is going to be proportional to the amount of lines that I have in my big sample. And there's mathematical principles like this that we can use to do things like, how do I know a 3-dimensional grain size distribution from a 2D section through my sample? Right? I need to be able to prove rigorously that if I take the areas of all my 2D grains, that it's going to relate to my volume distribution for 3D grains. Right? Because if I have perfect spheres, I'm not cutting all the spheres in the midpoint. Right? I'm cutting a sphere at some random height. So how do I know whether I'm looking at a small grain that I cut in the middle or a big grain that I cut near the top? Right? So there's some fundamentally challenging geometry that goes. It's really a fascinating field. There's some really good books on it if anyone becomes interested. Okay. So here we said that the dislocations, the yield strength is going to be proportional to the square root of dislocation density, right? And at low strains, we know that these dislocations are going to be more or less homogeneously distributed. So it's not too difficult to relate the expected separation of our pinning points to the dislocation density. Right? It's going to be related at the separation is going to be 1 over the square root of the dislocation density. Right? You can make a statistical argument very much along, that Buffon's needle game, where you drop a needle between parallel lines and you say what's the probability that the needle crosses a line based on how long the needle is and how far apart your lines are. Right? You can make a statistical argument along those same kind of lines. But what happens in reality to dislocation structure as our strains get higher and higher and higher? Right? They don't stay as nice, neat dislocation lines. They get all tangled and they develop a substructure. Right? And they essentially make a cell structure where you have these walls of very heavily entangled dislocations, and inside are relatively dislocation free. So here's copper. We see these walls, and aluminum, we see these cell walls where all the dislocations are packed together, and inside we don't see any. Right? And these walls consist of links of tangled dislocations meeting in nodes. And if you want to move things through, you have to extrude defects through this cellular structure. And how this comes about is really sort of an open question, right? It's kind of, I don't know whether it's cool or embarrassing to point out that we don't understand something this fundamental. We understand how individual dislocations move and interact. If give me 2 dislocations, I can tell you what their reaction is going to be and what the dislocation product is going to be and what kind of tangled mesh you're going to get. I can do X-ray diffraction experiments and tell you under this amount of strain how my dislocation density is going to evolve. What we can't tell you right now is how on earth this comes to be. When I have thousands or tens of thousands of dislocations, how they interact to form these cell structures, or why these cell structures are even energetically favorable. We don't know that. We do know, there's some really good simulation work from Jafar El-Awadi, along with the Air Force, where he's got probably some of the most advanced dislocation dynamics codes, and he's partnered with the Air Force, and they're using the best military supercomputers. And after running a simulation for a couple months of simulation time to a strain of a couple percent, they get something that kind of maybe sort of, if you look at it the right way, resembles some early cell structure. So we can't simulate it. It's too small for our coarse scale simulations. It's way too big for atomistic simulations. It's like the great frontier in metallurgy, this mesoscopic dislocation interactions, right? These are diffraction contrast in the TEM. So actually your contrast is coming from the strain fields around the... Yeah. Right. But these are both TEM images, right? And so, but what we can say, again, that stacking fault comes into play. The higher the stacking fault, the more tightly these cell walls are formed, right? And that the higher the stacking fault, the more diffuse the cell walls are to be, and you get a little bit more higher dislocation density in the material. Okay. So we talked about dislocations as being potent obstacles. Oh, I guess I should just say, obviously it makes more sense that it's harder to get a dislocation through the cellular structure than it is through a field of individual dislocations. It's not easy to derive what the pinning spacing should be, right? As it is with the square, but the square root law seems to magically hold still, right? That's another interesting question, is why does the Taylor-Hardening law hold when we have a cellular structure rather than individual defects? Damned if I know. But, so obstacles, that was dislocations as obstacles, grain boundaries as obstacles. I said there's only 4 things we can do to strengthen a metal, right? We can put in more dislocations, we can put in grain boundaries, we can put in precipitates, or we can put in substitutional solute atoms. So grain boundaries are also a very effective obstacles to dislocation motion, right? Remember, we said that a high-angle grain boundary is essentially just a very complicated array. It can be imagined as a very complicated array of dislocations. Right? For low-angle grain boundaries, we had these nice array structures. But as the character of the grain boundary got more complex, we didn't have a nice simple grain boundary model for it anymore. But anyway, as you can imagine, it's quite difficult to get a dislocation through a grain boundary. We don't know what's going to happen. Right? This is another really cool open area of research. Sometimes the grain boundary, the dislocations go right through like it doesn't matter. Other times they pile up. Other times they get absorbed and disappear. Other times they rebound off. Sometimes you have debris left behind where when the slip systems are not well aligned between the two grains. You have one dislocation type that comes in, another dislocation type that comes out, and your grain boundary structure has been altered, right? Again, another really important fundamental area of research that we still don't quite understand. We're all familiar with the Hall-Petch relationship, right? It says that the square root of the grain size is going to be proportional to the yield strength. Well, why does that happen? Why does, as the grain gets smaller, does our yield strength go up? What's that? Yeah, you're reducing your mean slip path, right? And we can think about this in sort of a geometric way. We know if this is an obstacle to defects, and I activate slip in this grain, this is a plastically soft grain. Remember, everything's anisotropic, right? So this grain might be much easier to, might have a much more favorable resolved shear stress than this grain. And so we start deforming this grain plastically. This grain is still elastic, right? We haven't activated any dislocations here yet. Schematically, we can think about stress dislocations piling up at this this interface, right? And we can calculate what the stress concentration due to this pileup is, right? These dislocations interact, right? And it's going to give us a higher stress in the region of these dislocations. And again, it's not super hard to calculate what the stress concentration is, but we're not going to do it for this class. But eventually what could happen is this pileup gets high enough that it activates some Frake read source in this other grain, right? So there's a strong neighbor coupling between plastic deformation in these grains, right? This is sort of a simple picture, and we can work through this to come up with an approximate, very hand-waving derivation of the Hall-Petch relationship. It's here if you want to look through it. Unfortunately, this model is really great. It's a really beautiful model from a theoretical standpoint, but we don't see a lot of detailed microscopy evidence that it's in any way, shape, or form right. We see pileups, but they don't quite behave in the way that this model would suggest. So this slide just gives a little bit of the maybe some other thoughts on how we can get at this Hall-Petch-like relationship when we consider emission and transmission of defects at the grain boundary, right? But it's not. Again, there's some extra stuff here. In the going forward, what I've decided to do to make it a little clearer, the notes for aluminum still have a lot of extra stuff in it, but I'm highlighting the main points, being like, because as I was preparing those, I was like, there's a lot of stuff here that I might say once and you'll never see again, but it would be great if you had it as a reference. So I'm trying to, going forward, separate out some things. But basically, general rule of thumb is that BCC and HCP have a much stronger Hall-Petch effect than FCC. Right. Right. That's the Hall-Petch coefficient. Right. And so strengthening can be very potent, but basically we have to get the grains pretty small. to really have a appreciable grain size effect, right? So grain refinement by severe plastic deformation, right? And this really sort of explains why nanograin metals become so strong in the way that they do, right? Because you've got a square root dependence, right? So you have something that you've got a huge effect when it's really small that tapers off pretty quickly. Okay. So really fast, I'm just going to introduce solid solution strengthening. Friday, we'll go through solid solution and precipitation, and then Wednesday we'll start into the meat of the course with the aluminum alloys. But again, one more time, dislocations interact to give rise to strengthening. In this case, it's a reaction with solute atoms, right? And we know that the stress field of a dislocation is long range. We've talked about that before, right? Solute atoms don't have exactly the same size and bonding as the main parent alloy. So they also have a strain field or a distortion associated with them, right? They're distorting their neighborhood slightly. You can imagine if you cram a bigger atom in, right, it's going to push the neighbors a little bit. So there's also a field there. And these stress fields can interact. And the bond strengths are a little different, right? So you can imagine, what did we say? That the energy of a dislocation is GB squared. So if the bond is slightly stiffer or slightly weaker from the solute to the matrix than the matrix, that's also going to have an effect when the dislocation gets near to it, right? It's going to change the energy of a dislocation. So that's the main idea behind solute solution strengthening. And then we can look at what those actual interactions look like. But basically it comes down to GB squared, right? If we put a stress field around it caused by a size distortion, or change the nature of the bonding when a dislocation hits it.